Hello everyone and welcome. This is General Chemistry 2, lecture number 19 on electrochemistry. This is the first lecture of Unit 4, the final unit in General Chemistry 2. This lecture covers a little bit of OpenStack section 7.2, which is a bit of Gen Chem 1 review, but you'll primarily find this material in sections 16.1 through 16.4 and 16.7. We're going to start by discussing electrons. So electricity and chemistry both involve the movement or transfer of electrons. In chemistry, electrons are transferred when one compound loses electrons and another compound gains those electrons. And I want you to recall from Gen Chem 1 that the loss of electrons equals oxidation, the gain of electrons equals reduction. So electrochemistry is therefore the use of chemistry to generate electricity. This involves the use of oxidation-reduction reactions, which are also known as redox reactions for the shorthand. So in these redox reactions, it is useful to be able to describe how electrons are transferred. We want to know which atom is losing electrons and how many, and also which atom is gaining electrons and how many. So if we look at an example single replacement reaction between zinc and copper sulfate to form zinc sulfate and copper, we can see here that the zinc is being oxidized. Its oxidation number is going from 0 to +2. Whereas copper is being reduced. Its oxidation number is going from +2 to 0. Remember that the substance that loses electrons gets oxidized and the substance that gains electrons gets reduced. We can also describe these compounds, these atoms, in terms of oxidizing agent and reducing agent. So we can say that the substance that loses electrons, the one that's being oxidized, we can refer to it as the reducing agent since it provides the electrons, which reduces the other substance. And similarly, the substance that gains electrons that is being reduced can be referred to as the oxidizing agent since it takes the electrons from the other substance. All right, the next 9 slides contain a brief review on assigning oxidation numbers. In my class, I don't go over these here for the purposes of this video. I'm going to just slowly go through these slides, but I will not be narrating. Again, this is a bit of Gen Chem 1 review, and I would urge you to review this material in more detail if you're having trouble with assigning oxidation numbers. All right, so now we're all caught up. Let's talk about the differing reactivities of metals. When metals form ions, they give away electrons, but not all metals do this as easily as others. So recall the term ionization energy. You learned about this in Gen Chem 1. This refers to how much energy it takes to ionize an atom, how much energy it takes to remove an electron. Remember that this trend increases going towards the top right. So the elements that have the lowest ionization energy, specifically the metals that have the lowest ionization energy, would be the ones further towards the bottom left of the periodic table. So if we compare these two oxidation reactions, which requires less energy, the answer would be the first one. They are potassium is number 19 in the periodic table towards the far left. Silver is number 47, is roughly in the middle. So though silver is one row down, one row lower, the potassium is much further to the left. So because of this, potassium has a lower ionization energy, and so this oxidation reaction would require less energy than this one would. So we can use this idea of ionization energy to analyze what is called the activity series. The activity series lists metals in order of reactivity from highest to lowest. These metals are ranked by their ability to give up electrons. Speaking in general terms here, metal A will replace ions of metal B in a solution if A is higher in the series than B. This means that A will give electrons to an ion of metal B. Basically, A will reduce B. So if we were to look at an example between the relationship of zinc and copper, we can see that zinc is higher on the activity series than copper is. It's more reactive. So zinc metal can displace copper ions in solution. And we could also say then that the zinc will reduce the copper ions. And so this is the basic version of that redox reaction between zinc and copper. So any metal that's further up the activity series can reduce the metals below it. Why does this happen? Why do redox reactions happen? This is because electrons will flow spontaneously, and spontaneously here does not mean instantaneous, but rather spontaneously means it will flow without the input of energy from the outside. So electrons will spontaneously transfer from a higher energy orbital on one atom to an empty lower energy orbital on a different atom. So suppose we have a high energy filled orbital on atom A, and then we have a low energy empty orbital on atom B. These electrons will naturally and spontaneously flow downhill. They will flow to the lower energy orbital that is empty. And so this occurs. So if we consider this redox reaction similar to the one we were just looking at, iron plus copper 2 plus forms iron 2 plus and solid copper. We could separate this into two half reactions where the iron is giving off 2 electrons because it's being oxidized, and the copper is gaining 2 electrons because it's being reduced. And if we were to look at the relative energies, if we were to look at an orbital diagram, iron has 2 electrons in a higher energy orbital, whereas that copper ion has an empty orbital lower in energy, and so these electrons will flow spontaneously downhill, so to speak, from iron to copper, which is why those electrons are being donated, and why the iron's being oxidized, the copper's being reduced. The reverse uphill reaction, however, will not occur. At least it will not occur spontaneously. You can't use copper to reduce iron. These electrons will not flow uphill. You would have to add energy to the system to get this reaction to occur. So a summary of redox terminology: iron is more reactive. It's the electron donor. It becomes oxidized. We can also say that it is the reducing agent. And then for copper, copper is less reactive, which makes it the electron acceptor, meaning that it gets reduced, and we can also describe it as the oxidizing agent. And oxidation and reduction, they must occur together. One substance cannot gain electrons unless another is losing them. All right, so let's look at this example reaction. We're going to identify the oxidizing agent, the reducing agent, and the number of electrons transferred. Let's start with aluminum. We can see on the left side that aluminum has an oxidation number of 0, and on the right side it has an oxidation number of +3. The aluminum is losing electrons, so we can say that it's becoming oxidized. Meanwhile, the lead here is going from an oxidation number of +2 to 0. Its oxidation number is increasing, meaning the lead here is gaining electrons, so we would say that the lead is being reduced. Aluminum is providing the electrons, so that makes it the reducing agent. Lead is taking the electrons, that makes it the oxidizing agent. So again, aluminum is losing electrons, it's being oxidized, and it is also the reducing agent. Lead is gaining electrons, it's reduced, which also makes it the oxidizing agent. Now to find the number of electrons transferred, we do need to write out the half reactions. So here's the half reaction for aluminum and the half reaction for lead. We can see here then on the left side we have a charge of 0. On the right side we have a charge of +6. The charge on both sides needs to match. So what do we got to do? We need to add 6 electrons to the right side of that equation to get the charge to balance on both sides. Down below, we have a charge of 0 on the right side, a charge of plus 6 on the left side, so we need to add 6 electrons to the left side as well, and we can see then that 6 electrons are being transferred. All right, next we're going to look at balancing redox equations. First, in acidic conditions. When balancing redox equations in acidic conditions, you should start by separating the equation into half reactions. Then balance atoms other than hydrogen and oxygen in each half reaction. Third, add water as needed to balance the oxygen atoms in each half reaction. Fourth, add H plus ions as needed to balance H atoms in each half reaction. 5, add electrons as needed to balance total charges in each half reaction. 6, equalize the number of electrons transferred between these half reactions. And finally, number 7, you can add those two half reactions together. Let's look at an example problem. This problem states, balance the following reaction in acidic conditions. So we've got permanganate plus bromide forms manganese 2 plus and bromine. So let's start by separating into half reactions. So we've got the manganese half reaction, we've got the bromine half reaction. Step 2, balance atoms other than hydrogen and oxygen in each half reaction. We can see here in this first one that manganese is already balanced, so we don't need to do anything to this first half reaction. In the second half reaction, we can see that the bromine is unbalanced, so I'm going to place a 2 in front of the Br minus here. So I have 2 bromine atoms on both sides. Next, add water as needed to balance oxygen atoms in each half reaction. In this first half reaction, I see that I've got 4 oxygen atoms on the left side, so I'm going to add 4 water molecules to the right side to balance the oxygen. And in my second half reaction, I see that there are no oxygen atoms, so I do not need to add water. Step 4, add H plus as needed to balance H atoms. Because I added water to the right side, now I have 8 H atoms on the right side of this first half reaction, so I should add 8 H plus ions to the left side to balance those hydrogens. And in the second half reaction, once again, there are no hydrogen atoms, no H plus added, or needs to be added here. Step 5, add electrons as needed to balance the total charges in each half reaction. So what I can see is I've got a charge of -1 from the permanganate, and then I've got a charge of +8 from those hydrogen ions, giving me a total charge of +7 on the left side. And then over here on the right side, I can see that I've got a charge of +2. So my charge on the left side is +7, my total charge on the right side is +2. I need to add 5 electrons on the left side to get the charge to balance. And then down below, I see that I've got a charge of -2 on the left side and a charge of 0 on the right side. So I need to add, therefore, 2 electrons to the right side to get the charge on both sides. One hint I do want to give here is that the electrons are always going to be added to the more positive side of each half reaction. So here it was +5 and +2. Add 5 electrons to that more positive side to make these numbers equal. Here we've got -2 and 0. Add 2 electrons to the right side to get these numbers to balance. Step 6, we need to equalize the number of electrons transferred between the half reactions. I've got 5 electrons here and 2 here, so I'm going to multiply this top half reaction by 2 and this bottom half reaction by 5, giving me 2MnO4 plus 16H plus 10H minus forms 2Mn2 plus and 8H2O. And then down below, I've got 10Br minus forms 5Br2 and 10 electrons, distributing that 5 to each of these species. And finally, step 7, add the 2 half reactions together. Anything that's the same on both sides can be canceled out, which in this case are the 10 electrons. And so I get a final answer of 2Mn2 plus 16H plus 10Br minus forms 2Mn2 plus 8H2O and 5Br2. And so this is the final answer. This shows the redox reaction balanced in acidic conditions. You do want to double check to make sure that it's balanced, so you should have the same number of atoms of each element on either side. You should also have the same total charge on either side. And if you want to pause the video and check, you should find that this reaction is balanced. All right, Now, what if we want to balance these redox equations in basic conditions? You follow the same 7 steps you did for balancing the reaction under acidic conditions, and then there's just a few additional steps at the end. For every H plus that appears in the final overall reaction, add OH minus to both sides of the reaction. When H plus and OH minus are present on the same side, combine them to form water, and then cancel water on opposite sides of the equation as needed. So if we want to go back to that previous equation, actually, sorry, this is a slightly different question, so let me walk through it. Separating this reaction into half reactions, we have the same initial permanganate half reaction, MnO4 forms Mn2+. Our other half reaction is different. It's HC2O4 forms CO2, so we've separated it into half reactions. Now I need to balance the atoms other than H and O. In this first half reaction, M is already balanced. In this second half reaction, the carbon's unbalanced. I've got 2 carbons here, 1 carbon here, so I'm going to add a coefficient of 2 to balance the carbons. Step 3, add water as needed to balance the oxygen atoms. So that involves me putting 4 H2O on the right side to balance the oxygens. In this second half reaction, the oxygens are actually already balanced. There's 4 on both sides, so we're good there. Step 4, add H plus as needed. So for that first half reaction, we added 8 H plus to the left side. For this second half reaction, I've got 2 hydrogens on the left side, so I need to add 2 H pluses to the right side. Fifth, add electrons as needed to balance the total charge. So for this first half reaction, that involved us adding 5 electrons to the left side to get the charge to balance. For this second half reaction, we can see that we have a charge of 0 on the left side. We have a charge of +2 on the right side. That means I need to add 2 electrons to the right side of this half reaction. Another hint I want to give here is that the electrons should always be on different sides of the 2 half reactions. That way they cancel one another out when you add these half reactions back together. All right, now you want to equalize the number of electrons transferred. So we've got 5 here and 2 here, meaning we need to multiply the first half reaction by 2 and multiply the second half reaction by 5, and so that work is shown here. Step 7, add the 2 half reactions together. We'll find that the electrons transferred, and it gives us the reaction 2MnO4 plus 16H plus forms 5 H2C2O4 forms 2Mn2 plus, 8H2O, 10CO2, and 10H plus. And then notice here that we actually have some H plus on both sides, so these can cancel out. So these 10 will cancel out with 10 of these. So there should be no H plus on the right side and 6 H plus on the left side. Alright, so if I had asked you to balance the half reaction in acidic conditions, you would be done. This would be your final answer. But because you're being asked to balance it in basic conditions, you've got a couple more steps to do. First, what you need to do is for every H plus that appears in the final overall reaction, you need to add OH minus to both sides. So I've got 6 H plus on the left side, so I'm going to add 6 OH minus to both sides. Then, if you've got H plus and OH minus present on the same side of the reaction, you can combine them to form water. So the H plus the OH minus forms H2O. So we've got 6 H2O now on the left side, and then those 6 OH minus are now on the right side. And then your final step here is cancel water on opposite sides of the equation as needed. I've got 6 water molecules here, which will all cancel with 6 of these water molecules, leaving just 2 H2O on the right side. And then our final answer, hold on, sorry about that. Okay, sorry, I had a small mistake in my slides here. I forgot to add in, there should be a 2 H2O remaining on the right here. And so this would be the final answer. 2MnO4 plus 5 H2C2O4 forms 2Mn2 plus, 10 CO2, 6 OH minus, and 2 water molecules. And this, again, this is the final answer for balancing this redox reaction in basic conditions. Just don't forget to double check that it's balanced, meaning same number of atoms on either side and same total charge on either side. All right, so this is approximately the halfway point of this lecture. So I've got 5 practice problems for you to try here. So I would encourage you to pause the video and give these problems a try. And then you can find the answers to those problems right here. I'm actually going to cut the video off here and split it in half. So this is the end of the first half, and I'll see you in the next part for the remainder of the electrochemistry lecture.